Welcome to week two. This week we're going to discuss pointers, references, strings, and functions. Now, these are going to be uh, very important for your C++ programming. This is sort of um, so in the first week, we have sort of the fundamentals. Uh, this week, it's another set of core features of C++ that you have to really understand. Now, the tasks this week, um, well, first you should keep working on your lab and assignment for the week one and get them done. Um, then you should be reading the chapters 6 through at 10. Now, this is the material that even though you probably will learn something new, um, but the basic concept, I suppose you should already have some understanding from your prerequisite classes. And let's start with the chapter 6. So chapter 6, we're actually going to learn pointers and references. So what is a pointer? Now, here's a simple example. So first we declare a variable called number is a long type, long integer, and initialized with 1, 2, 3, 4, 5. L here is the indicates is a long integer literal. And suppose this variable is stored in memory at a location 1000. Now here is the hexadecimal notation. So it's not really 1000 in decimal representation, but this is a hexadecimal, so it's 1000. And assuming, well, long, here we're assuming this is going to be 4 bytes length, and so this is what the number 1, 2, 3, 4, 5 might look like in memory. Now we declare another variable that has a type long with a asterisk here, right? Now this asterisk is actually indicates this is a pointer type. So the way to read this, it's pointer to long. So the type of the P number is pointer to long. So when we define this variable, we also initialize it with something. Now, this ampersand here is an address of operator. So this is the way to read this is the address of a number. So that operator, if you go back to the operator precedence table that we introduced in week one, you'll see it's pretty high up there in terms of precedence if you use this in the expression. So address of operator in front of a variable gives you the address. So in this case, it gives you 1000 hexadecimal address. So the P number, though, that is also a variable. So that might be allocated somewhere else in memory. Let's say is at the memory location 3020. Well, whatever that is, decided at a runtime by the operating system, basically. And this pointer variable has a value. What is the value? The value is address. So the value of this P number, the pointer, is actually the address of the variable number, which is 1000. Okay. So you see this pointer variable has a value of an address, which points, basically this pointer points to another memory location. And that memory location may also have a value now because the type is not complete if you just say this is some kind of pointer. The type is complete when you say it's a pointer to long or to some type. So the complete type for this variable is long with asterisk when you represent it in the C++ in code. And this, but the way you read it is basically this is a pointer to long, and that's basically this pointer. So we have this is essentially what a pointer is here. So this is a fairly straightforward. Now the pointers support some arithmetic. Specifically, you can use addition and subtraction. They are not the same as the integer arithmetic or the numbers that you know about. This is a little different, and because the way the pointers are supposed to be used. A pointer points to some type, and that type, maybe is a fundamental type, and maybe it's some more complicated object. But when you're doing the arithmetic on the pointers, you're moving the pointers element by element, object by object. So it's assuming you're using a pointer to work on an array, and you have a contiguous block of memory, you have multiple elements of the same type, and then you're using the pointer, usually represented with an arrow, and you want to sort of iterate over a range of those elements. So when you're doing +1, +2, you're moving sort of at the element level, not at the byte level, right? Not so even though the value of the pointer is an address, it's also an integer, right? But it's not interpreted like that way. So this, as I explained, when you use the +1, you're moving that by one more object. So if your pointer points to a double here as an example, if the double is represented with 8 bytes, so your pointer +1 is going to move 8 bytes each time. So it's moving like one double each time. So your p-value here points to, in this case, actually, the specific example, we actually declare first an array of 10 doubles. And now we initialize a pointer with the name of the array, which is interesting. Well, it turns out the name of the array represents the address of the first element or the 0th element of that array. So the name of the array is it's almost like a pointer. Since pointer basically it has a value, they store addresses, and then so the name of an array also stores the address, but they're not necessarily the same. Well, for starters, an array type, right? The information about the size of the array is also stored, right? So that we know, okay, how many elements is this array allocated with? A pointer doesn't have a size here, right? That's one. Secondly, you cannot change the value, sort of the address of the values. Once you declare a an array, the address will be set. It's fixed. Well, the pointers is meant to be changed. I mean, it's usually the way you use it is basically use it as a variable, and then you change the value or the address, right? The variables that the pointer point to, over some kind of range, or you point to some variable that you just typically want to change. But you can also have const pointers. A const pointer, um, I don't even have the example right here. I think we can take a look at a programming example shortly. A const pointer, as an example, would be the pointer value cannot be changed, meaning the pointer variable is fixed. It points to that same location. It cannot change. That's a const pointer. But a pointer can also point to not only to a variable, but also a const variable, which is not the same as a const pointer. Const pointer says the address cannot change, but const variable means the value cannot change of the variable. But the pointer itself, if it's a variable, is not a const pointer, then you can still change the pointer to point somewhere else. But you cannot change the value uh, of the pointer. Basically, you cannot change the value the pointer points to. So it's an indirection, is what it is. We're going to see some more concrete example. Perhaps it's a little more clear. In fact, let's actually take a look at the, let's see if this is a good example. Pointer notation. Okay, this is an example to look at that. So example 605. So here's some examples. This program is actually calculating primes, just calculating, let's say the first 100 primes and then print them out. So we're not gonna I'm not gonna analyze the detailed every line by line. The book has a very good explanation. I just want to point out the places where we're using the pointers. So here, the primes. Now, so the primes, see here, this is actually is an array, right? Is an array of size max, and max is a const variable of 100. So it's basically 100 long values in this primes array, and then every value, well, actually, we're defining the first value, well, the 0th element is 2, and then the rest will be 0 as the initialization in this format. And this, as I said, this is it's almost like, not the same, it's almost like a const pointer. And so you can use the pointer notation, the things you treat this almost like a pointer and use it that way. And so the primes, thinking this like a pointer, you use a pointer arithmetic plus count. And then you know this postfix form of the increment operator. And so basically the value that you with this expression, they just use the address of primes plus the count. So that's me moving however many elements over toward the higher end of the array. And you do this is the asterisk here is an operator to dereference the pointer. So the dereferencing gives you the variable the pointer points to, and or the data element that it points to. And the data element, so this is equivalent to, if I write this in the, subscript notation, right? That's what you're familiar with previously. It'd be similar to, it's basically equivalent to this, right? This particular statement is equivalent to this. But here's just to show you the pointer operations. In fact, the subscript operator is pretty much implemented this way, actually. It's implemented using the pointer arithmetic. And so anyway, when you have this thing on the left-hand side of assignment, you are modifying the content of that memory location. If you're using this on the right-hand side of assignment, then you're reading the content of that memory location. Okay, so you can do it on both sides. And notice this on the left-hand side, you can also use an expression. This is exactly what, this whole, we have the expression here. And this is the expression. You have an operator. This is a unary operator. This is the reference unary operator. Well, of course, after this expression is evaluated, the variable count will be incremented, right? This is a postfix form. And that's that one. So over here, this is actually another example. So we're seeing here primes plus I and dereference that. This is essentially equivalent to, equivalent to primes with a subscript I. Okay. And then we're using this as an argument to this format function. And so this is reading the value from that memory location. Now remember, plus I is not adding that value to the address, but rather to add that many element positions to that memory address. You're moving to like I elements over toward the higher end of the memory location. Okay. So that's that. Let's go back here. Dynamic memory allocation. Now, this is an example. So now we see something new here. So there's this new thing here. This is called a new. Now, new is an operator. So you may have noticed that some operators are words, some operators are symbols. So either way, they're all operators. So there's a new operator. What this does is it will allocate a um, a data element. Here we have a double. So here we're allocating a double, on the in memory, of course. Where is it allocated? Now recall previously we talked about the process address space. You have sort of different sections of the memory where you may store different kinds of variables, like global variables, static variables. You put that into the data section. And then you have the text section of that memory space. You put your code in. And then there's also a dynamic area where you have an arrow that sort of like indicates you can dynamically change, increase or decrease. So that's really what that is. This dynamic portion is where all the, most of your variables are going to be using that area. When you use this new operator, you're basically using a portion of that memory space to store your variables. And so, in fact, here, we don't really have a sort of a permanent variable for this particular operation. So that's actually a temporary, creates a temporary. So if you look at the new operator, right, we're not really, so anyway, this is going to create a double on the in the memory dynamic memory region of this of the memory for this program. But this part of the region usually is called the free store. In the C++ standard, it's called free store. Some language call it the heap. So this in the free store, you have this allocated, and then we have that basically assigned to this pointer variable value. Now pointer variable value, so now is initialized with an object, and that is allocated on the free store. And then this is the allocation. Now, one thing that makes this special, by the way, As opposed to automatic variables, you have this function. When the function returns, automatic variables are automatically deallocated from the stack. And versus this, when you allocate something on the dynamic memory on the free store, they are not going to go away unless you deallocate it. So the deallocation is done through another operator called delete operator. So if you once you declare this variable you put on the free store dynamic memory, then you use it, and at some point you have to deallocate it so that the memory will be released back to the free store, which will be used for other purposes. If you don't release the memory back and you keep holding on to it, and then you may have a memory leak. So that's one of the issues we're going to talk about in a second. So once you deallocate, so this is a when you're dealing with the pointers, the pointer, by the way, it holds on to the this object here. Um, you need to deallocate it because now it points to um, a memory that's on the free store, dynamically allocated variable. You gotta delete it or deallocate it after you're done using. And then after this, you want to reset the pointer to a null pointer. Now, null pointer is a keyword. Um, it simply means the pointer points to nothing. Okay. Don't use integer 0, use null pointer. Okay. So even though it might be just a 0 as an integer behind the scene, but you're supposed to use null pointer. Um, so that is a simple example. And another pair of dynamic memory allocation is for arrays. So you can use the new operator to allocate an array. Like here is the 100 doubles on the free store. Then after you're done using, you need to release that. Otherwise, the memory is occupied and lost. It will be not available to useful purpose. And so when you delete it, you delete with a square bracket after that as the operator to delete a pointer that points to a dynamically allocated array. So that's how you release it. And then after releasing, again, you need to set the pointer to a null pointer. That is just a good habit to do, even if you're not going to do anything afterwards. So the other example would be, let's say we've studied, how to use a vector. The vector is a wonderful library object, a class that you use this to hold on to elements that you don't know the size of. Um, but you can also create a vector on the free store, dynamically allocate a vector and use the new operator. And then so you create a vector object. In fact, a vector of integers, right? A vector of int on the free store. So that is, so you have this pointer point to that. So by the way, whenever you use the new operator, the return of that expression is going to be an address. So you have to assign that to or initialize another pointer for this because the pointers are designed to hold on to addresses. And so you got a pointer here. Here, remember, notice that we're using the auto keyword to let the compiler deduce the type. Um, this asterisk, so indicating this is the pointer to let the compiler, this is the pointer. Uh, and then the reference, the pointer, basically then you're accessing the vector that's on the free store. So you're accessing that object, and then you call the uh, member function pushback to basically to add element to the end of the vector. So this is one way to do it, and here there's another way to do it. Another way to do it is use the pointer with a indirect member selection operator. This is called a member selection operator. So it only makes sense when the data is pointed to an object that has member functions or member variables. We're going to study a class uh, next week, in fact. So these two forms here are equivalent. So you use data with this arrow and then push back. So this is another way. Obviously, this is more intuitive with the arrow because the arrow indicates, looks like this is a pointer. This is how we usually illustrate a pointer on a diagram. Drawing some kind of memory location, we use pointers, the arrows to indicate that are pointers. So this is a more intuitive way of doing it. So the pointers, the way we've seen so far, they are called the raw pointers, just to differentiate them from the smart pointers that we're going to look at. And the raw pointers are dangerous. And in fact, again, so anybody knows a little bit about C++ kind of knows that the pointers are one of the things that can easily get wrong, and that's kind of source of many bugs. And these are not necessarily unfamiliar terms. Your pointers could be dangling, meaning you have a pointer variable that contains an address, but the data, the object at that address has been um, deallocated. So that memory address doesn't mean anything anymore now. It's just some junk data. And you could potentially deallocate a pointer multiple times. So that's a problem, right? You have deallocated, let's say you have a pointer that pointed to some object, and then that's deallocated. Now, once it's deallocated, you need to deallocate again. Now, remember that once it's deallocated, that whatever is there, it's just, junk data. That address doesn't really mean anything to this program anymore. And then, or potentially that same address could be used for something else because the other parts of the program also needs to allocate something. So this will cause typically a crash in the program. The allocation deallocation needs to match. So if you use the array form of a new to allocate, and then you need to delete or deallocate with the delete square bracket to deallocate an array pointer to array. And the non-array form of the new needs to match the non-array form of delete. So they are in pairs. If they're mismatched, then there's a problem. Memory leaks, there's not much to explain because if you hold on to the memory you already don't use anymore, you just keep holding on to them and then eventually run out of memory. Fragmentation of the free store. Now the free store, so this is the place where you allocate and deallocate as your program runs that, um, depends on how your program is written. You could be using a lot of it, and so you have constantly have some allocation and deallocations. And then there's no magic here. That area, that region of memory has to be managed somehow. So there's some sophisticated data structure or algorithms that are that are used to manage this area of the free store um, efficiently. But still, there's a fragmentation issue. Potentially could be a concern. But this is, I would say, you normally don't need to be concerned with this. There's some rare cases that you might encounter such a thing. But there are ways to solve that problem. It's a little bit more advanced how to manage memory. You can have your own memory management algorithms. The C++ library, for example, many of the containers allow you to plug in your own allocator, which is your own algorithm for managing memory. So in some rare occasions, you might consider that, but that's sort of a little bit advanced topic. So the book provides a simple tip. So basically, don't use those raw pointer allocation, deallocation uh, operators. So these operators, if you use them, that's because you're writing some low-level code that actually is dealing with, um, for example, memory management, and then that you may have that kind of stuff. But generally speaking, don't use them in your code. Avoid them. So instead, of course, there's definitely need for using pointers. So, but don't use the raw ones. Use smart ones. The smart pointers. Here's a a smart pointer. It's called a unique pointer. So the unique pointer, um, the feature of that is it's a single owner. So the pointer points to some object, and the unique pointer is designed such that you can only have a single unique pointer that points to that underlying object at any moment. You may transfer the object to a different unique pointer, but then the older unique pointer will be basically uh, nullified, and so basically it will no longer be valid. So this is used in a situation where um, this is the feature that you desire. Um, So here is the syntax how you might do it. There's obviously you can use the new operator, but again, as we suggested, don't use new operator in your day-to-day programming. Instead, use this library, a standard library function called a make unique. Use this make unique function, and you might notice there's a angle bracket here. This is indicating as a type variable, a type parameter for that, because this is a what so-called function template. In fact, we're going to study function template towards the end of the week. So anyway, this is providing the standard library. Use this make unique to create to initialize your unique pointer. So here we're making a unique pointer to a double, initializing a smart pointer data with that value. Now there's another form of a make unique function that's called make unique default init. So because this function will do sort of zero initialization, but this function will not do that. It will use the default initialization, which is usually means there's nothing you will do. The position may contain the whatever is trying to make. The underlying object could be just a random, like it's not initialized, so to speak, but that's the default initialization. Um, So as an example here, we're making a unique pointer points to a double array and with n elements. The size of double array is n, but we're not initializing the array elements. So the elements, they contain random values. So that's the usage where you may use this form of the function if you don't want to initialize. Okay. There's another type of a small pointer. It's also commonly used. And this small pointer basically allows you to share the underlying object with a multiple pointers. The owner, when I say owner here, owner means is an object of a share pointer or an object of a unique pointer. This pointer. So one thing I did not mention, this is also explained in the book. When you use a unique pointer object can be used almost like a raw pointer because the operators that you use with the raw pointer, they are all implemented on those unique pointer or the share pointer, small pointer classes. So that's why you can use them. And so the way this is managed now, what is the whole good thing about small pointer anyways? Small pointer really, it takes care of deallocation. So you don't ever have to worry about deallocating them or forgetting them or forgetting, or worry about mismatch or all these problems that we just talked about, the dangers of a raw pointer. They are taken care of because how the small pointers are designed. And there's no magic here, and you're gonna know how that's done when we study the classes. So here, the share pointer, it will maintain a reference count. So basically, it will keep track of how many references are there that point to the underlying object. So it will deallocate the object when there's nobody or no pointer points to it. So basically now the object is no longer needed, it will be released. So here's an example here to use the share pointer. Now here I'm using the auto keyword for compiler type deduction. And the make shared, that's kind of analogous to make unique. Make shared for making shared pointers. And here I'm making a shared pointer that points to a double, initialize it with a 999.0. So the type will be deduced to be a shared pointer of double. Well, shared pointer to double, that's basically, again, this angle bracket here is the type parameter. And of course, you can also use that to share a pointer for arrays. So this is similar to what you see above for the unique pointer. Same thing. There's a third type of a small pointer. It's called weak pointer. Now, a weak pointer is linked to a shared pointer, but it does not, when you use a weak pointer points to the same underlying object, it will not increase the reference count. A typical usage of a weak pointer is to break that reference cycle. And that, well, of course, on your day-to-day programming, you're probably not going to be seeing much of the weak pointers. You don't really use this much. In a certain design of some classes, you may consider this, but it's kind of rare. So we don't talk too much about this one. So the commonly used ones are unique pointers and the shared pointers. And then references. What are they? Now, by the way, references, you don't see references in C. This is a purely C++. So reference. So first you have to have a variable. So we have a variable that has a memory location. And Then you can create a reference to that variable. A reference is just like a alias, except that this data ref is not, you cannot have this point to a different variable once you have this initialized. So it's like a non-modifiable alias to data. So wherever data is used, you can also use data ref. Now, what's the difference between this? Because the reference is dealing with addresses too. In fact, they are implemented with pointers, but they're not the same as pointers. In fact, they just probably come with, the idea is they come with restrictions. So for example, a reference must be initialized. You can't just create a reference that points nowhere. Reference has to refer to something. It's alias of some variable. A reference cannot be modified. It's like a const pointer. So we talk about const pointer. Const pointer basically means that you cannot change the address of this point. Well, the value of a pointer is an address. You cannot change the value of the pointer. And so the reference cannot be modified. So it's a bound, essentially it's like it's a bound to a variable, to memory location, and you cannot change it. So when you need to access its value, you don't dereference like a pointers need to use the asterisk. The asterisk is also called the indirection operator. That is what's used to dereference a pointer, but you don't do dereferencing with the references because the reference is like an alias to a variable. You use this as is. So a typical usage of reference for right now, it'll have a much more usage. We're going to see a lot more of the references later on. But for right now, in previous program, we'll talk about one of the places where we talk about, say, you can access the elements in a range-based for loop, but how do you modify it? You could not modify it without references because if you let's say you remove this ampersand here, this t variable, the range variable, is going to get a copy of the element as it iterates through that range. So we cannot, if you modify the copy, you're not modifying the actual element in that range. So if you do want to modify the element in the range, then you use reference. This is one example how to use references. And so here's an example here where let's say we're converting Fahrenheit to Celsius. And we're modifying the values within these temperatures. Let's say it's an array, okay, or maybe it's a vector, whatever that might be. It's a range. And so now we can modify it. So remember, you see these references used on the left and on the right, just like a regular variable, okay? Except this time is not making a copy. It's a reference to the specific element during each iteration, okay? So let's summarize the chapter. A pointer is a variable that contains an address. So it's like an indirection. It's an address to some other thing, some other variable that's in memory. And a basic pointer is also called a raw pointer. And then the address of a variable can be obtained with the address of operator. If you have a regular variable, you want to know the address of it, use this address of operator. And typically this may be used to initialize a pointer. Now, a pointer is dereferenced with the indirection operator asterisk to access its value. So the this is actually the indirection operator is used to dereference a pointer so you can access its value, and this Dereferencing can be used on the left-hand side and right-hand side of the assignment. So if you use on the left-hand side assignment, that means you're modifying this value, whatever that location is. The indirection member selection operator, or the arrow operator for short. So typically people call it the arrow operator. This is used to access a member of an object. For example, the vectors pushback method function that can be used this way. Now this is the notation for accessing the member through a pointer. If you're accessing the pushback, for example, for the vector, from a regular variable, not a pointer, and then you use the dot, which is a member access operator, member selection operator, not the indirection directed version, which is through the pointer. So it's a little different. And the raw pointers support this addition, subtraction, arithmetic operators. And then this pointer arithmetic is different from the, for example, integer arithmetic, and semantics are different, okay? Dynamic memory allocation, deallocation operators are those four, actually two pairs, new and delete, new for array and delete for array. So these are the dynamic memory management operators. Now the suggestion is don't use them because there are a lot of pitfalls. And for example, you may have a memory leak, you may have a dangling operator, so you have a bunch of issues that makes people think C++ is difficult. One of the reasons because these raw pointers, they can be dangerous. Now, a smart pointer is preferred, and a smart pointer is essentially an object. It's the design of smart pointer. It's a class, right? So you make an object of those classes, like and then you can use them just like a raw pointer. And you don't worry about the allocation of memory; they're automatic. So two commonly used small pointers: unique pointer and shared pointer. And a reference to an alias for a variable that represents a permanent storage location. Now, permanent is relative. This just means that it's not a temporary. Temporary, for example, you have an expression, and during the evaluation expression, the compiler may make some temporaries, but this permanent storage location could be an automatic variable that has a location, basically has an address. That's really what this means. Now, we have seen an example of a reference loop variable in a range-based for loop that's used to modify the elements. You can also have a reference to const loop variable. And you're going to see a lot more example later on, by the way, so we're going to skip looking at this further. So that's that. And there is actually another example that I want to, let's point this out about the small pointers. Small pointers are defined in this memory module or this header. If you would not use the module version, it would be just a header, the memory. And so here's an example that we'll kind of look at this example. This is where you're seeing this, use this standard function, make shared. And then this is interesting here. So we are actually making a shared pointer to a vector of double. And these shared pointers are this day records. You see we're pushing, adding this to records, which is a vector. So the records of vector is a vector of shared pointers, okay? It's a vector of small pointers. And so I'm using a using statement here just to make a better name for this long thing, which is a shared pointer to a vector of double. And this is essentially a little program that used to, you can run this, okay? The example is in. And you just to again this is just some basic example it used to calculate the average temperature of the day, and then you can store as many days as you want. So asking you input those temperatures from a command line. And so just kind of show you an example, and then to print out the temperatures, you see there's two for loops here. It's a range-based for loop. And now here I'm showing you this syntax here. Remember that we analyzed this range-based for loop syntax. You could do a init statement here. This is an example of init statement. So the scope of the stay variable remains in this for loop body, okay? And this is where you can use the stay, not outside. And so I made some slight modification from the code that's in the book. Okay, what else here? Yeah, so that's it. I just want to point this a couple of things out. Hopefully is useful. Let me know if you have any questions. Thank you.